relative dominance. Relative dominance is the area taken up by species 1 divided by the total area taken up by all species. By all species. So this is our absolute dominance. If we had other tree species out here, we would take the area taken up by all trees, that's the denominator. The area taken up by our tree species, that's the numerator. And just as with relative density, we end up with a percentage. Keep in mind that for relative dominance measures and absolute dominance measures, we can arrive at high abundance as measured by dominance by either having a lot of individuals that are all very small, or I could have one large individual that takes up the same amount of space. So unlike density measurements, we really don't necessarily know anything about the number of individuals because it's the collective area taken up by all members of the species, a few or a lot. Okay? Right, that should bring us to our final measure of abundance, which is frequency. I mentioned before, frequency is kind of a measure of common or rareness of a species. So we could have a community that we're investigating. We go out, establish quadrats at random within this community. And then look to see whether species 1 is present in the quadrat or not. So here I have 11 quadrats, and my species is present in 4 of them. Quadrats where species 1 is present divided by the total number of quadrats. That's 4 divided by 11. That's our absolute frequency. Unlike our other absolute measures, absolute frequency is a percentage. Absolute dominance, absolute density are not percentages, but absolute frequency is a percentage. Now, when we go to calculate out the relative frequency, what we're doing is taking the absolute frequency of species 1 and dividing it by the absolute frequency values of species 1 plus the absolute frequency of species 2 plus absolute frequency of species X. And this relative measure is also given as a percentage. Okay. All right, so 3 measures of abundance: density, dominance, and frequency. We can think about each of them either as absolutes or relatives. Absolute just tells us something about that species, whereas the relative abundance values tell us something about our species relative to everyone else. Okay? All right, let me show you an example of how this might be used. Let's take a particular community. Let's go back to that work that was done by Jamie, that student of mine, back in 2010. And we have information about the species in each quadrat. Right, we have this matrix of values here. And let's go ahead and calculate out the absolute density of each of the species. Okay, so we have for quadrat 1, for species 1, we have a particular value, but we also have that value for each of the quadrats. So if I sum up the entire column, I get a measure of the absolute density overall across all 245 quadrants. Okay, so let's go ahead and plot this up. Okay. Now, the way it's typically plotted up, absolute density here, that's the number of stems, in this case it's plants, number of stems per area. And here would be the number of, oh, sorry, got this backwards. Absolute density will be on the y-axis as number of stems per area. And then along the x-axis, we're going to put our individual species. Now, to make this easier to interpret, what we're going to do is sort the absolute densities of all the species and put the highest one over here. So this would be species 1 with the highest overall absolute density, and then we'll plot all the subsequent species in descending order of absolute density. Okay? Now, when you do this for a community, you get something very interesting resulting from this kind of work. So let me show you what it looks like for the bluffs. I know it's hard to read these things, but the individual text here is just particular species. So from the work at the bluffs, Caniza canadensis is the most abundant species. The total number of individuals per area is like 325, and there are 245 quadrats. So I hope you can see that there's greater than one of these individuals on average per quadrat. Okay, it's a very abundant species as measured by density. The next one's Stellaria media, right? And we can keep going on as we go along here, but what I hope you'll notice is that this curve has a particular shape to it that is kind of like this, right? The shape of this curve is kind of like this. Okay, this is called a J curve. I don't know why. To me, it looks more like an L curve, right? If you flipped it backwards, maybe it would look a little bit more like a J this way, but it's called a J curve. Okay? And the idea is that for communities in temperate zones, doesn't matter what community you look at. You could look at phytoplankton, you could look at fish, you could look at plant species, small mammals, rodents in a forest or whatever, that there are typically a few very abundant species. On my plot, I'd say, wow, look at that, I've got 3 species that are very abundant, but most of the species in the community are not abundant, as measured in this case by density, right? Common And these species, I would say, are more rare, right? Maybe overall I collected 5 of them, or 6 of them across 245 quadrats. If I had 245 quadrats, that means that on average, they're in approximately 40 of the quadrats on average. No, I got that backwards. If there's only 6 of them, right, they're only present, only 6, right, 6 over 245, I did my math backwards. That would be the percentage of quadrats that they actually occur in. So 6, that's about 2.5%. Okay, so they only occur in about 2.5% of the quadrats. Okay? In that case, that's a rare species. It's present in that old field, but there's not much of it. Now, I want to finish through the community stuff, and then I do have a little bit where I want to talk about kind of an ecologist's understanding of why things are rare and why things are common. And we'll put that in context with some speciation stuff. But for right now, we do know some reasons why species might be more rare and more common. When we talked about a pathogen like the pathogen that causes Dutch-Elm's disease, that individuals might become more dispersed in space, right, moving toward a more uniform dispersion, not as common. And in a place like this old field here out at the Erie Bluff State Park, we might not expect to find very many of a particular species, maybe because of pathogen interactions, right? When they become too close together or too clumped in space, pathogens do them in and they end up becoming more dispersed in space, pushing them to become rare. So one of the reasons why species might be rare has to do with interactions with other species. But again, we'll come back to this later. So I'm going to go ahead and call it a day here, and then next time we'll start into species diversity and then do a little bit of succession. All right, so take care.